Imagine this. You're standing at the edge of the universe, you reach out your hand, and then
What?
a wall? Infinite emptiness? Another universe entirely? The answer is far stranger than you think. Tonight, we're tackling one of humanity's most profound questions, a question that has haunted philosophers, kept scientists awake at night, and might just blow your mind. Where does space stop? And here's the twist. It might not stop at all. Or maybe it stops in a way that defies everything you thought you knew about boundaries, edges, and endings. Welcome back to The Sleepy Scientist. I'm here to take you on a journey through the cosmos, one that will stretch your imagination like the universe itself stretches through space and time. Whether you drift off peacefully or find yourself too captivated to sleep, you're in for something extraordinary. Before we launch into the void, hit that like button and subscribe. It helps this channel grow. And drop a comment. Where are you watching from and what time is it? Are you cozy in bed in Tokyo at midnight? Or pretending to work from your couch in Sao Paulo at 2 p.m.? I love seeing our sleepy science community scattered across the globe. Now settle in. Get comfortable. You don't need to remember every detail. Just let the words wash over you like cosmic radiation. This video is for educational and relaxation purposes only, not medical advice. Ready? Let's begin our voyage into the vast unknown, the living fabric of reality. For most of us, space is simply nothing. A void, an empty stage where planets orbit and stars shine. But here's the truth that will change how you see everything. Space is anything but empty. For centuries, we imagined space as Sir Isaac Newton did, as an absolute, unchanging arena, a fixed grid where time ticked uniformly and objects moved predictably. Then came Albert Einstein, that wild-haired genius with his chalkboard covered in equations, and he shattered that simple picture forever. According to Einstein, space isn't a passive backdrop at all. It's a living, dynamic fabric that bends, twists, and warps in the presence of mass and energy. Space and time aren't separate entities. They're woven together into a four-dimensional tapestry called space-time, and this fabric actually responds to what's happening within it. Picture a trampoline. Place a bowling ball in the center and watch the fabric dip. Now roll a marble across the surface. Instead of traveling straight, it curves around the depression. That's gravity in Einstein's universe. Massive objects like stars and planets don't pull us like magnets. They warp space-time itself, and we're simply following the curves. Earth doesn't pull you down. It curves the space around it, and you're rolling into that dip. The quantum hum of empty space, but it gets stranger. Even in the darkest, loneliest corners between stars, space is never truly empty. Thanks to quantum mechanics, we now know that empty space is actually buzzing with activity at the smallest scales imaginable. Space is filled with quantum fields, not things in space, but space itself. Every particle in existence arises from its corresponding field. Electrons come from the electron field, photons from the electromagnetic field. And here's the mind-bending part. Even when no particles are present, these fields never stop moving. They fluctuate constantly, producing tiny momentary particles that appear and vanish like cosmic fireflies. This jittery energy is called vacuum energy. It's like the surface of a pond. From far away, it looks calm. Get close, and you see ripples, disturbances, hidden motion. The vacuum isn't empty. It seethes with potential. Virtual particles pop in and out of existence in fleeting pairs. They can't be directly observed, but their effects are measurable. They influence how electrons behave around atoms and even contribute to the mysterious dark energy that's pushing our universe apart faster and faster. So no, space isn't just where you lose your keys or send your thoughts during awkward conversations. It's alive with structure and movement, even when nothing visible meets the eye. And here's the real kicker. Space itself can expand. Not things moving through space, but space itself stretching between them. That idea underpins our entire understanding of cosmology. A comforting thought. There's something deeply comforting in all this. It means the universe isn't a cold void. Even in its quietest, darkest moments, there's still something happening. A soft background hum, like the crackle of a fireplace or leaves rustling on a still night.
Space isn't the absence of matter.
It's a physical entity with properties of its own. It can bend and stretch, expand and ripple. It has energy. It even has temperature. The vast emptiness between galaxies hovers just a few degrees above absolute zero, faintly warmed by the leftover glow of the Big Bang. When we ask, what is space? We're not talking about an empty void. We're talking about a rich, structured fabric that connects every atom, every galaxy, every living being. Space is not where things happen. Space is one of the things that happens. The horizon we can't cross. Imagine standing on a quiet hilltop under a clear night sky. The universe stretches in every direction, seemingly endless. But here's the reality. There's a cosmic limit to what you can see, not because the universe ends there, but because light simply hasn't had time to reach us from beyond. This is the observable universe, the part of the cosmos we can actually detect through light, radiation, or gravitational waves that have managed to travel to us since the beginning of time. That word observable is crucial. It doesn't mean everything outside it doesn't exist. It just means we haven't been lucky enough to see it yet. The expanding horizon you might logically think we could see about 13.8 billion light years away. After all, that's how old the universe is, and light travels at, well, the speed of light. Because space itself expands, the boundary is actually much farther out. The observable universe has a current radius of about 46.5 billion light-years in every direction, making it roughly 93 billion light-years across. Yes, you read that right. Even though the universe is only 13.8 billion years old, the distance to the farthest galaxies we can see is more than 3 times that. Why? Because space has been stretching the whole time. Think of it like this. Imagine placing raisins in bread dough and baking it. As the bread rises, the raisins move apart. Now imagine a photon of light emitted by one raisin toward another, right as baking begins. By the time the light arrives, the bread has expanded. The photon's journey wasn't across a static distance, but a growing one. The cosmic horizon. This brings us to the cosmic horizon. Not a wall you'll bonk into like a cartoon character, but a gentle fading of information. Beyond this horizon, light from distant regions hasn't had enough time to reach us since the Big Bang. And here's the bittersweet truth. As time goes on, some galaxies are moving away from us so quickly because the space between us is stretching that the light they emit now will never reach us. Not in trillions of years. They're receding faster than light itself, not because they're breaking any speed limit, but because space is stretching too fast. The universe is slipping out of our grasp. Everyone's personal universe. What's humbling is that everyone, everywhere, has their own observable universe. If you were standing on a distant galaxy 10 billion light-years away, your cosmic bubble would overlap ours slightly, but would include regions we'll never know. The observable universe isn't the universe, it's just our slice of it. And what a slice! Roughly 2 trillion galaxies, each containing millions to trillions of stars. Some photons reaching your eyes tonight began their journey before Earth had even formed. That ancient glow is a time machine, a message from an epoch long past. Beyond the cosmic horizon, space might continue forever. It might curve or loop back on itself, but we'll never know. Not with light, not with any signal bound by the speed of causality. There's a kind of peace in that limit. We don't have to understand or control the whole universe to find meaning in it. Sometimes it's enough to sit beneath the stars and know you're part of something far larger than yourself. Every star is a time capsule. When we look up at the night sky, we're not seeing the universe as it is now. We're seeing the universe as it was. Every star, every galaxy is a time capsule. The farther away it is, the older the light we're seeing. A light year is the distance light travels in 1 year, about 6 trillion miles. When you look at a star 100 light years away, the light reaching your eyes left that star a century ago. You're seeing it as it was when your great-grandparents were young. Some galaxies we observe are billions of light years away. The light from them began its journey before our solar system existed, before Earth formed its oceans, before the first microbe drew breath. This is what astronomers call look-back time. How far into the past we're seeing. If a galaxy is 8 billion light years away, we're seeing it as it was 8 billion years ago. More than half the age of the universe, ghosts and fossils. In a strange way, space is full of ghosts, echoes of what once was. Some galaxies we see may not even exist anymore. They might have merged, changed shape, run out of star-forming gas, or drifted beyond the reach of light due to expansion. What we see is a cosmic fossil record written in photons. Redshift, the cosmic Doppler effect. As light travels through expanding space, it stretches. This phenomenon is redshift. Like how an ambulance siren drops in pitch as it moves away, light's wavelength lengthens when its source recedes. By measuring redshift, astronomers can determine how far away a galaxy is and how long its light has been traveling. High redshift means a very distant galaxy and a very ancient glimpse into the early universe. This redshifted light carries clues about the structure, age, and history of the cosmos. Every color-shifted photon is a messenger from the past. Telescopes are time machines. When you look through a telescope, you're not just seeing things more clearly, you're seeing them more deeply into time. A backyard telescope shows Jupiter's clouds from 40 minutes ago. A powerful observatory reveals a galaxy as it appeared 500 million years in the past, when life on Earth was still experimenting with fins. Then we have the heavyweights, Hubble, James Webb, and their successors. These instruments peer so far that they capture the first galaxies to ever form, just a few 100 million years after the Big Bang. It's ironic. To understand the universe's future, we spend most of our time staring into its past. A museum made of light, the universe as we experience it is always a little out of date. It's like watching a film that's still being edited, with scenes arriving one at a time out of order, some from nearby, others from across the cosmic abyss. But that delay is a gift. Without it, we could never piece together how everything came to be. The slower arrival of ancient light lets us see different evolutionary stages all at once. We're living inside a museum made entirely of light. Every time you look up, you're gazing into a time machine. The light brushing your eyes may have started its journey before Earth's first tree, first cell, first breath of atmosphere. Next time you see a star twinkling, remember, you're not looking at it as it is. You're looking at a version preserved in time, a glimmer of history still racing through darkness. Living inside the fog, picture yourself in a field at dawn. The grass is wet with dew, and a soft fog rolls across the horizon. You can only see a short distance, maybe a few trees, a distant hill, but beyond that, everything fades into blur. That's what it's like to live inside the universe. No matter how powerful our telescopes become, there's a limit to how far we can see, shaped by time, distance, and the expanding cosmos. These limits are cosmic horizons, and they define the boundaries of our observable universe. The particle horizon, the first, is the particle horizon, the maximum distance from which light could have reached us since the universe began. It marks the outermost edge of the observable universe. Since the universe has existed for about 13.8 billion years and space has been expanding, the furthest distance light could have traveled to reach us today is around 46 billion light years in any direction. But don't mistake this for a wall. There's no glowing border with a no entry sign. It's a limit woven into time itself. Like standing on a shore looking out to sea. You can look as far as light allows, but you'll never see beyond that gentle curve. The event horizon next is the event horizon of the universe, not to be confused with the kind surrounding black holes. In cosmology, this refers to the boundary beyond which events can never affect us, no matter how long we wait. Anything beyond this point is retreating faster than the speed of light due to expansion. That light, no matter how persistent, will never catch up. It's like trying to send a message to someone on a raft drifting downstream faster than you can throw. No matter how hard you try, the message will never be delivered. The cosmic event horizon is thought to be around 16 billion light years away. There are regions we can see now, but if they emit new light today, that light will never reach us. We're watching galaxies slip away. Visible today, destined to fade forever. The cosmological horizon, finally. There's the cosmological horizon, which encompasses these observational limits and reminds us that horizons aren't just visual. They're deeply tied to the physics of the universe itself. These horizons are constantly shifting. As the universe ages, the particle horizon grows. More light has time to reach us. But because of dark energy and accelerated expansion, the event horizon shrinks in relevance. More galaxies move beyond our reach. The universe becomes a place of increasing isolation, not because it's empty, but because light from distant corners is falling behind. The beauty of limits. There's something haunting yet peaceful about these limits. They're a quiet reminder that we're not omniscient observers. Our view is shaped by cosmic history and the strange properties of space-time. Some regions will always remain a mystery, not because we lack technology, but because of the very nature of space and Tim. These unseen realms aren't behind a curtain waiting to be pulled back. They're beyond the reach of information, forever unknowable. And yet, even within these boundaries, we've learned so much. We've mapped galaxies, measured background radiation, traced the fingerprints of the Big Bang. The horizons don't limit our imagination, they frame it. The discovery that changed everything not too long ago. People believed the universe was pretty steady. Galaxies out there, stars shining, everything more or less staying put. Then Edwin Hubble made a game-changing discovery. While studying distant galaxies, he observed that their light was consistently red-shifted, meaning they were moving away from us. And the farther away they were, the faster they seemed to recede. This wasn't random. It was a pattern, a law. Space itself was expanding. The raisin-bred universe. This isn't galaxies zooming through fixed space like race cars. It's stranger and more elegant. Space itself is growing. Imagine space as dough and galaxies as raisins. As the dough bakes and rises, it stretches in every direction. Each raisin finds itself farther from the others, not because it's moving on its own, but because the dough between them is expanding. There's no central raisin, no preferred direction, just uniformly growing dough. This is how the universe works. Galaxies aren't rushing outward, they're being carried as the fabric of space stretches. That's why, from every galaxy's point of view, everything else appears to be moving away. The universe isn't expanding into anything. It's just expanding. Einstein's greatest blunder. This idea was so radical that even Einstein had to revisit his equations. Originally, he'd added a cosmological constant to make the universe static. When he heard about Hubble's findings, he called it his greatest blunder. Ironically, the concept made a comeback in explaining dark energy. Rewinding the cosmic clock, if galaxies are moving apart now, they must have been closer together in the past, much closer. This led scientists to the idea of a hot, dense beginning, the Big Bang. The term is misleading. It wasn't an explosion in space like fireworks. It was the rapid swelling of space itself, everywhere, all at once. No center, no blast radius. You can't point to a location and say, that's where the Big Bang happened, because it happened everywhere, including right where you're sitting. The acceleration mystery. The expansion is still happening today, nearly 14 billion years later. But here's the surprise. It's accelerating. Scientists had assumed gravity might slow things down. Instead, they found a mysterious force, dark energy, causing the expansion to speed up. The dough isn't just rising, it's rising faster and faster. No one knows exactly what dark energy is. It might be an inherent property of space or a field we don't yet understand, but it now dominates the energy budget of the universe. A poetic truth. There's poetry in this. The universe began with everything close together, dense and unified. Over time, it expanded, cooled, formed stars and planets, and all the ingredients for life. And now it continues to drift outward, stars aging, galaxies moving apart, space stretching into the unknown. If there were sound in space, maybe it would be the soft creak of rising dough, the occasional pop of a bubble, the peaceful hum of a universe becoming itself. The universal speed limit in physics. There's a hard and fast rule. Nothing can move faster than light, about 299 million meters per second. According to Einstein's relativity, this is the universal speed limit. And yet, astronomers have observed galaxies moving away from us faster than the speed of light. It sounds like physics is panicking, but don't worry, everything's fine. The universe isn't breaking the rules. It's playing a clever game with them. Space stretches, not galaxies. Galaxies aren't flying through space like comets. Instead, space itself is expanding, and galaxies are carried along with it. Think of space as a rubber sheet with dots on it. Stretch the sheet, and the dots move apart, not by crawling across the surface, but because the surface itself is growing. This is how galaxies can appear to recede faster than light. They're not breaking the speed limit. Space is doing the legwork. The treadmill analogy. Imagine you're on a treadmill that's speeding up. You try to walk towards someone at the other end, but the treadmill moves backward faster than you can walk forward. Eventually, the distance between you keeps increasing. Not because you're walking too slowly, but because the ground is working against you. In the universe, light tries to travel through expanding space, but in some regions, space expands so rapidly that light never makes progress toward us. Relativity only forbids objects moving through space faster than light. It doesn't say anything about how fast space itself can grow. Cosmic inflation take, for example. Cosmic inflation, a mind-bending moment just after the Big Bang when the universe expanded at a staggering rate, far faster than light. In less than a trillionth of a second, it grew from something smaller than a proton to something the size of a grapefruit or larger. This faster-than-light swelling didn't break any rules. It was space doing the expanding, not particles racing through it. Inflation smoothed out the early universe, ironing away wrinkles. It explains why the universe looks so uniform in every direction, despite distant regions never having time to exchange information. Lost beyond the horizon, even now, billions of years later, space continues to grow, carrying distant galaxies farther away. Some are now receding faster than light. Not because they're speeding up, but because space between us is growing faster than light can close the gap. This means there are regions of the universe we can never see. No matter how long we wait, their light will never reach us. These galaxies aren't lost because they're moving too fast. They're lost because the road between us is stretching out faster than signals can travel. A peaceful melancholy. There's a certain melancholy in this reality. The universe is full of stories we'll never hear, stars we'll never see, galaxies we'll never know existed. Yet this, too, is part of the wonder. The fact that we've glimpsed so much of the universe's past is nothing short of miraculous. From a tiny planet orbiting an unremarkable star, we've caught ancient photons in mid-flight, pieced together the origins of galaxies, and traced the faint afterglow of the Big Bang, all in a universe where space moves faster than light. Beyond the box, when we think about the universe, it's tempting to picture it like a big box, a vast space with edges, maybe floating in something else. But the real shape of space is far more subtle and fascinating. Space isn't necessarily flat, like a tabletop. It might be curved, positively, negatively, or just ever so gently flat. The geometry of the universe has deep implications for how it evolved, how it behaves, and whether it might curve back on itself or stretch forever. Three main possibilities: a flat universe like an infinite sheet of paper. Parallel lines never meet. Triangles add up to 180 degrees. Travel in a straight line, and you'll keep going indefinitely. 2. A closed universe shaped like a sphere, or its 3D equivalent. Space curves back on itself. Set off in a straight line, and you'd eventually return to your starting point, like walking around Earth's surface without falling off. 3. An open universe shaped like a saddle or a Pringle. Space curves outward, parallel lines diverge, triangles add up to less than 180 degrees, travel forever, and you'd never loop back. A critical density. These shapes are tied directly to the universe's overall density and energy content, specifically how much matter and energy exist compared to the critical density needed for balance. If actual density, equal density closed, positively curved. If actual density, equal density open, negatively curved. If densities match flat, measuring the shape, how do we measure this? Through the cosmic microwave background, the ancient light traveling since shortly after the Big Bang. By analyzing tiny fluctuations in this faint glow, scientists determine how space bends light over vast distances. So far, evidence suggests our universe is very, very close to flat, close enough that any curvature is too small to detect. It's like standing on a massive plane that might have a slight bend over the horizon, but as far as you can see, it's pretty straight. Finite but unbounded. Here's where it gets really interesting. A flat universe can still be infinite or not, and a closed universe can be finite but unbounded. Take the surface of a sphere. It's finite. You can measure its total area, but it has no edges. You can walk around a globe forever and never fall off because there is no edge. Now apply that to a three-dimensional version. That's what cosmologists mean by finite but unbounded. A closed loop, a self-contained bubble of geometry. This kind of space doesn't have a border. There's no place where the universe ends and something else begins. It just loops back on itself. Cosmic geometry and fate geometry also affects the universe's fate. Closed universe. Gravity might eventually slow expansion, leading to a big crunch, open or flat universe. Expansion could continue indefinitely, cooling into a gentle fade, though with dark energy pushing things apart faster. The big crunch seems unlikely. A comforting mystery. What's particularly comforting? No matter the shape, we're part of it. Whether the universe loops, drifts, curves, or stretches, we're woven into its structure. Our atoms obey its geometry. Our light traces its curves. Our thoughts echo through its halls. We don't just live in space. We are space folded into itself. Life on a balloon's surface. Imagine you're a tiny creature living on the surface of a balloon. You can walk north, south, east, west, but you can't dig down or float above. Your entire world is that two-dimensional skin, curved but seamless. This is the magic of curved space. It plays by rules that don't match everyday experience, yet makes perfect sense once you understand the rhythm. Geometry on a sphere, on a flat surface like paper. Geometry behaves familiarly. Triangles add up to 180 degrees. Parallel lines never meet. Walk straight, and you go forever. But on a sphere's surface, a planet or balloon, geometry acts strange. Triangles can add up to more than 180 degrees. Parallel lines converge at poles. Walk in a straight line, and you eventually loop back. From your limited perspective on the surface, space feels infinite. But in reality, it's finite and curved back on itself. Scaling up now, take that concept and scale it up. Imagine our entire universe as a three-dimensional version of that balloon surface, curving in ways we can't easily visualize because it curves in higher dimensional space. You and I live inside this 3D space, moving through it without seeing the outside, just like the balloon creature never sees the air around the balloon. The expanding balloon. In this analogy, galaxies are dots drawn on the balloon's surface. As the balloon inflates, dots move apart, not by crawling across the surface, but because the surface itself stretches. This is what cosmologists mean by universe expansion. Space itself is growing, carrying galaxies with it. If the universe is truly curved and finite, traveling in a straight line long enough might eventually bring you back where you began. No edge to fall off, the loop closes smoothly. No special center. The balloon analogy helps us understand why there's no center of the universe. Just as there's no single center on a balloon's surface, the universe doesn't have a central point from which everything expands. Expansion happens everywhere at once. Every point moves away from every other point as it inflates. Pick any spot and call it here. The view looks the same in all directions. Intrinsic curvature, the balloon analogy isn't perfect. It's a model to help our 3D brains grasp higher dimensional ideas. The balloon surface is 2D, embedded in 3D space we can picture. But if our universe is curved, it might curve in higher dimensional space we can't observe directly. It's not floating in a larger container. Space doesn't need an outside to curve. It can curve intrinsically by its own properties. This is one of Einstein's great insights from general relativity. Space and space-time have shape and structure, and that shape can evolve over time. Light's curved path curvature affects light's path too. In curved space, light doesn't travel in straight lines as we understand them. It follows the shortest path available, called a geodesic. That's why massive objects like stars and black holes can bend light. Gravitational lensing. We're seeing a web of light moving through curved space, stretched and bent by the mass of everything around it. The expansion only affects large scales as the balloon inflates, distances between galaxies grow, but the galaxies themselves don't expand. That's because expansion happens on large scales between objects not gravitationally bound. Our Milky Way, solar system, even Earth, none are getting stretched. Expansion only takes hold in the great emptiness between galaxies. What's driving it? We now believe dark energy, a mysterious form of energy inherent to space itself, is causing the universe to accelerate. The balloon isn't just inflating, it's inflating faster with every breath. A gentle metaphor next time you see a balloon rising. Give it a nod. It carries within it the shape of something much greater, a gentle curve, a stretch of space, and the quiet idea that maybe the place you're headed is also the place you started. Only now you've traveled the universe to get there. The biggest question, infinity. The word itself feels like it should echo. It's vast, mysterious, intimidating. But what does it really mean when we ask? Is the universe infinite? Is space truly unending, stretching on forever without a final border? What we know, everything we've measured about the large-scale structure, suggests the universe might be infinite. Observations of the cosmic microwave background reveal that space is extremely close to being flat. In general relativity, a flat universe could very well be infinite. If it isn't, it's at least much, much larger than what we can observe. The observable versus the actual, the observable universe stretches about 93 billion light years across. But beyond that, it could keep going. Galaxies upon galaxies, cosmic structures we'll never detect, entire regions forever beyond our view. We can't actually prove or disprove whether the universe is infinite because we're confined to observational limits. Or like ants on a beach seeing only sand in every direction. For all we know, the beach stretches across a continent, or maybe it ends a few dunes over. We just can't see far enough to know. Infinity isn't a number. Infinity isn't something you measure with a ruler. It's a concept, an idea. And in science, concepts need evidence. You can never directly observe infinity. You can only look for signs that space shows no signs of curving back or ending abruptly. So far, we've looked in all directions and seen no detectable edge, no sudden drop-off, no cosmic fence. But that doesn't mean one doesn't exist. It just means it's beyond what we can see. The peculiar consequences. If space is truly infinite, then the amount of matter is also likely infinite. That means an endless number of stars, planets, comets, clouds of dust, and yes, potentially even life. Somewhere out there, there might be another planet just like Earth, maybe with sideways trees or oceans that sparkle with strange colors. Maybe with creatures asking the same question, repeating patterns in an infinite universe. If matter is distributed uniformly, the laws of probability suggest patterns will eventually repeat, which means somewhere out there, there could be a version of you, or several, some nearly identical, others who chose different breakfast cereal this morning. Don't worry, you won't bump into your cosmic doppelganger. These regions are likely so far away, they're forever unreachable. Caution and humility. There are good scientific reasons to be cautious about assuming infinity. We have only a finite sample to work with. Cosmologists remain open to the idea that space might be very large but still finite, curving gently back in ways we can't yet detect. There's also the question of time. The universe might be infinite in space but finite in duration. It had a beginning, the Big Bang. Even if the cosmos is endless in extent, philosophical implications infinity challenges how we relate to the universe. Most things in daily life have limits. Infinity breaks that mold, removing boundaries and opening endless possibility, inspiring and overwhelming at once. Some ancient thinkers were deeply uneasy with infinity. Aristotle believed the universe must be finite because actual infinities were too strange to accept. Even today, some debate whether true infinities can exist in the real world. The value of contemplation, whether or not the universe is infinite, contemplating it has value. It stretches the mind, invites humility, reminds us how small our perspective really is. When you look up at the stars, you're peering into a mystery so vast that our boldest measurements barely scratch the surface. Maybe the universe is infinite, maybe not. Either way, it's more than enough to fuel our questions, stories, science, Andrea. And the most wonderful part? You don't have to know how far it goes to feel at home in it. You're already woven into its fabric, a flicker of thought on the edge of the observable, glowing softly in a cosmos that may never end. Our obsession with edges, there's something irresistible about the idea of an edge. We grow up with edges, walls, fences, sidewalks. Everything we encounter seems to stop somewhere. So when we think about the universe, it's natural to imagine it must stop too. Surely space must come to an end somewhere. But here's the twist. Space doesn't actually need an edge. It can be finite in size without having a boundary at all. Earth's surface as model picture, the surface of Earth. Walk in a straight line in any direction, and you eventually circle back to where you started. You wouldn't fall off anything. You wouldn't hit a wall. No signpost reading, "End of Earth, please turn around." The surface is finite but unbounded. It loops back on itself seamlessly. Three-dimensional version. Now take that idea and expand it to three-dimensional space. Imagine living inside a volume that wraps around itself like a globe's surface does in 2 dimensions. Keep moving forward in a perfectly straight line, and you might eventually return to your starting point, never encountering a wall, cliff, or any kind of edge. This isn't science fiction. It's a perfectly valid cosmological model. Finite, unbounded space. The torus example, one classic shape is the torus donut. Its surface is two-dimensional. You can walk around it forever without leaving the surface or hitting boundaries. It loops both horizontally and vertically. Now imagine a three-dimensional version where space loops in multiple directions. You could start at one point, travel in a straight line, and after a very long time find yourself right back where you began, like a galactic boomerang. Now imagine a three-dimensional version where space loops in multiple directions. You could start at one point, travel in a straight line, and after a very long time, find yourself right back where you began, like a galactic boomerang. Video game worlds, another helpful analogy. Classic arcade games like Pac-Man or Asteroids. Move your character off one edge of the screen, and they reappear on the opposite side. The game world is finite in size, but edges don't behave like real-world walls. They connect. These are two-dimensional versions of toroidal space. Cosmic wallpaper. In theoretical cosmology, some models propose the universe could have a topology that loops in subtle ways. We might not notice unless we looked far enough in just the right direction. There's even been speculation that if the universe is small and curved just right, we might see repeated patterns in the cosmic microwave background, like mirrored wallpaper from the Big Bang. So far, we haven't found clear signs of this repetition, but the idea hasn't been ruled out. No outer surface needed. The deeper truth: the universe doesn't need an outer surface or surrounding void. That's a very human way to look at space. Something sitting inside something else. But space isn't embedded in a bigger thing. It is the thing. Even if the universe is infinite, it still doesn't require an edge. Infinity isn't a place, it's a property. You don't need to find the last number to know one doesn't exist. Philosophical headaches. Edges create philosophical problems. If there were an edge, what would be beyond it? More space? Something else? A blank nothingness? The moment you introduce an edge, you introduce a paradox. If there's something beyond, space hasn't really ended. If there's truly nothing, how can it be said to exist? A universe without edges avoids this confusion entirely. It just is. Not a box, but a melody. This paints a picture of a universe far more subtle than a giant box. It's not an object you can lift the lid on or peek around the side of. It's more like a melody that plays itself forward, wrapping around dimensions with no final note, no ending chord, just an endless variation. In that melody, there are no hard edges, only connections, curves, and continuations. The oldest light before stars, before galaxies, even before atoms properly formed, there was a glow, a soft uniform light spread across the universe like warm fog. It wasn't a spotlight or flash. It was quieter, gentler, like dawn's first rays before anyone opens their eyes. Some of that light is still with us today. We call it the cosmic microwave background, CMB, the oldest light anyone can see, a whisper from the very early universe. The hot, dense beginning about 13.8 billion years ago, the universe began in a hot, dense state. In its earliest moments, space expanded rapidly, spreading energy like batter in a pan. At first, the universe was a blinding soup of particles and radiation. Photons bounced around constantly, trapped in fog of charged particles. Light couldn't get very far before being scattered. like trying to shine a flashlight through dense cloud. Recombination. The fog lifts then, about 380,000 years after the Big Bang, the universe cooled enough for protons and electrons to combine into neutral hydrogen atoms. This moment, poetically called recombination, changed everything. With fewer charged particles to scatter off, light was suddenly free to travel. The fog lifted. The universe became transparent. The first light broke loose. Light that's been traveling since that ancient light set free has been traveling ever since. It fills the universe in every direction, stretched out by billions of years of expansion. Once a searing blast of ultraviolet energy, it's now cooled to a gentle microwave hum, a whisper instead of a roar. But it's still there, passing through your room this very moment, like a soft, invisible breeze from the beginning of time. Accidental discovery. We first discovered the CMB almost by accident. In the 1960s, two radio astronomers, Arno Penzias and Robert Wilson, used a large horn antenna to study radio signals. They kept detecting persistent background noise wherever they pointed. They cleaned equipment, double-checked math, even removed pigeons nesting in the device. But the noise remained, steady, uniform, strangely cosmic. What they'd stumbled upon was the afterglow of the Big Bang, the cosmic microwave background, predicted by theory and now detected. A cosmic blueprint since then. Space missions like COBE, WMAP, and Planck have mapped the CMB in astonishing detail, giving us a high-resolution picture of this ancient light. It's more than just a glow. It's a cosmic blueprint, a snapshot of the universe when it was less than 500,000 years old. Tiny fluctuations at first glance. The CMB looks incredibly uniform, same temperature and brightness everywhere. But zoom in, and you see tiny fluctuations, warm and cool spots, just millionths of a degree different. These gentle ripples aren't imperfections. They're the seeds of everything. Tiny density differences that over billions of years would grow into stars, galaxies, and you. Clues about the shape. Those variations are clues. They tell us how matter was distributed early on and let us test theories about how space and time unfolded. Even the shape of the universe leaves fingerprints on the CMB. If space were curved like a sphere, saddle-shaped, or flat, those geometries would subtly distort how light travels. By measuring fluctuations, scientists infer large-scale structure. So far, all signs point to a universe that is flat. The universe's lullaby. There's something deeply soothing about imagining that glow, a soft wash of ancient light, not blinding, but calm and even. You can't see it with your eyes, but it's always present. It's like the universe's own lullaby, still playing after all these years. If you tuned in with the right radio, you'd hear it everywhere, not as a song, but as faint static warmth, a constant presence woven into space itself. A gift in photons in a universe filled with mystery, the CMB is something solid we can measure, map, and understand. It reminds us we don't need to chase the edges of space to learn about its beginning. Sometimes the answers are already floating around us, waiting patiently in the glow. When imagination meets physics, is there a true edge to the universe, some ultimate boundary where space just stops? While mainstream cosmology leans toward a universe with no hard edge, some speculative theories and thought experiments nudge open the door to stranger possibilities. Brain cosmology start with the idea that our three-dimensional universe could be a brain, short for membrane, floating in higher dimensional space, an offshoot of string theory. In this picture, our universe might be a vast 3D membrane existing within a higher dimensional bulk. We're confined to this brain. All particles and forces except gravity are stuck here like bugs on a soap bubble. Gravity might leak into surrounding dimensions, one reason it seems so weak compared to other forces. If this is correct, our universe could have an edge, not in 3D space, but in the higher dimensional bulk we can't perceive directly. From our view, everything seems continuous and edge-free. But from the perspective of a hypothetical five-dimensional being, we might look like a cosmic disk with boundaries at the rim, cosmic domain walls. Then there are domain walls, boundaries between different regions where laws of physics might be slightly different. These walls are predicted by some theories of symmetry breaking in the early universe. Imagine space went through a phase change, like water freezing, but didn't freeze the same way everywhere. Some regions froze with one set of rules, others chose a different path. The borders could form domain walls, massive structures stretching across space. In most models, these disappeared quickly, but some scenarios imagine they could still exist, lurking in deep space like silent sentinels. Passing through one might be undramatic, or like stepping into a parallel universe with slightly different chemistry. Bubble universes. Some thinkers wonder if our entire universe might be the inside of a bubble. Literally, a bubble of space that formed during cosmic inflation. Picture the early universe frothing with quantum fluctuations. In some regions, inflation stops and a bubble forms with its own properties. The constants of nature, strength of gravity, number of dimensions. Each bubble is a universe unto itself. This is eternal inflation, leading naturally to a multiverse, a foam of bubbles, each with unique physics. In this view, there's a kind of edge where our bubble meets the inflationary background or where it might collide with another bubble. But collisions would be beyond rare. If we're a bubble in vast cosmic foam, our neighbors are too far away to ever meet. Gödel's rotating universe in 1949, Kurt Gödel came up with a solution to Einstein's equations describing a universe rotating as a whole, not individual galaxies spinning, but the entire fabric of space-time slowly twisting. In this strange model, time and space curve such that you could travel along a specific path and arrive back at an earlier point in time, essentially a time loop. Gödel's universe has no edges but blurs the line between boundaries of space and boundaries of cause and effect. What's more disorienting, a wall at the universe's end or the ability to meet yourself before you were born? Note, Gödel's rotating universe doesn't match observations. Our universe isn't spinning that way, and time loops remain theoretical. But the model stretches our minds, reminding us equations sometimes allow worlds stranger than fiction. The holographic principle. Another wild idea. The universe might be like a hologram, not in the sci-fi sense, but mathematically. According to the holographic principle, everything happening in our 3D space might be encoded on a distant 2D boundary, like how a hologram stores a full image in a flat surface. The true edge of our universe isn't a wall or border, but a boundary where fundamental information is stored. We're not talking simulations, just a different way of describing the same physics. The idea emerges from string theory and black hole thermodynamics. The deeper message, the message behind all these theories, isn't that we'll find a physical wall with a no entry sign. It's that space might have limits and boundaries in ways that don't look like what we're used to. Edges might exist in higher dimensions in initial conditions or in the information underlying everything. They might not look like walls. They might look like changes in physics, curvature, or the rules themselves. Living in the mystery, it's entirely possible. We live in a universe with no edge at all. But it's also possible we're brushing up against ideas that feel like edges, limits of what we can know, observe, or describe. And that's a kind of boundary too, isn't it? Maybe the cosmos loops quietly. Maybe it stretches infinitely. Maybe it perches on the surface of a higher dimensional bubble. Or maybe it's shaped like something we've never thought of before. The universe could be endless, not just in size, but in possibility. The ultimate what if. Understanding this universe is challenge enough. Billions of galaxies, black holes, cosmic background radiation, space that might curve or stretch forever. But every now and then, cosmologists like to stir the pot and ask an even bigger question. What if this universe isn't the only one?
Welcome to the multiverse hypothesis, one of the most fascinating, bizarre, and thoroughly speculative ideas in modern physics.
The basic idea, very simply, it suggests there might be more than one universe, perhaps many more, maybe even infinitely many. Universes with different physical laws, different particles, different timelines. Universes where cats walk on ceilings, gravity flows sideways, or your high school haircut turned out much better. An important caveat before we go too far, there is no direct evidence for other universes. None. We haven't seen them, measured them, or waved to them across a dimensional fence. The multiverse is a framework, not a conclusion, a way of thinking that arises naturally from certain theories, but still lives firmly in speculation. That said, the idea isn't as wild as it sounds. There are several different versions, each with its own flavor. The bubble universe model. The first is the cosmic multiverse or bubble universe model, coming from inflation theory. According to this view, inflation didn't happen uniformly. It could have created many separate bubbles, each forming its own universe, expanding and evolving in depth. Each bubble might have its own laws of physics, some too strange to support matter, others with entirely different particles, forces, or dimensions. We happen to live in one of the lucky ones where conditions are just right for stars, planets, and late-night cosmic contemplation. In this model, our universe is like a single soap bubble floating in cosmic foam. Other bubbles might exist, endlessly drifting, forever separate from ours. The quantum multiverse. Then there's the quantum multiverse, from the many worlds interpretation of quantum mechanics. This version says every time a quantum event has multiple possible outcomes, all of them actually happen in separate branching universes. In one universe, you hit snooze this morning. In another, you got up early and made pancakes. In yet another, you tried making pancakes but accidentally discovered teleportation instead. Each branch is a new reality created by every possible choice and chance. This isn't just a thought experiment. It's a serious interpretation developed to avoid the awkwardness of wave function collapse. But we can't jump between branches. There's no interdimensional train station. And yes, somewhere in infinite branches, you probably have a mustache, even if you've never grown one. The mathematical multiverse. There's also the mathematical multiverse, proposed by cosmologist Max Tegmark. This is the idea that all mathematically consistent structures exist as physical realities. In other words, if it's mathematically possible, it exists somewhere. That includes not just universes with different particles, but ones with entirely different logical rules, universes where pi has a different value or time flows in a spiral. It's bold, almost mystical, and probably impossible to test, but it's compelling to think math itself could be the fabric of existence, spawning every possible variation like an infinite library of cosmic blueprints. The criticism these multiverse ideas face criticism, and rightly so. One of the biggest issues is falsifiability. If other universes are forever inaccessible, how do we study them? How do we know they exist? Science works best when we can test predictions and refine models. When talking about realms unreachable by any signal, it's hard to apply usual scientific tools. Some physicists see the multiverse as a warning sign, theories stretching beyond useful limits. The anthropic response, others argue the multiverse helps explain why our universe has the properties it does. If there are countless universes with different constants and laws, it's not surprising we live in one where life is possible. It's cosmic survivorship bias. We exist here because here is where existence is possible. It's like rolling dice at a casino with infinite tables. Most produce nothing interesting, but at one table, by pure chance, the dice land just right. That's the table we're sitting at. a stretch of imagination whether or not other universes exist. Pondering them stretches our imagination. It encourages thinking beyond what we can see, reminds us reality might be far broader and stranger than expected. It invites humility in the face of what we don't know, and boldness in exploring what we might someday learn. And really, isn't that what science is about? Not just answering questions, but discovering bigger ones. Even if we never find another universe, even if this one is all there is, we've already proven human curiosity can reach across galaxies, through time, and into ideas as vast as the multiverse itself. So whether you believe in a single cosmos or an infinite stack, whether you prefer one timeline or a branching forest of quantum possibilities, remember, somewhere in the multiverse, you're doing something brilliant, unusual, or inexplicably involving a llama. And in this universe, you're here, thinking about space and quietly wondering what else might be out there beyond the veil. That in itself is cosmic magic. Circling back to the beginning, where does space stop? It's the question that brought us here, whispered softly at the beginning like a child asking if the sky has an end. After wandering through galaxies, curved dimensions, cosmic microwave whispers, and edges that may or may not exist, we find ourselves gently circling back, still wondering. What we've learned that space doesn't behave like a room or a box. It doesn't need walls to be complete. It can be infinite or finite and unbounded, stretching, looping, curving, folding in ways we're only beginning to understand. Carrying galaxies away faster than light, not because they're moving, but because space itself is growing. We know there's a limit to what we can observe, a cosmic horizon beyond which light hasn't yet reached us. But we don't know what lies beyond. Maybe it folds back on itself in a gentle arc we'll never see. Perhaps our universe is one bubble among many, drifting in higher dimensional seas. Or perhaps the multiverse is just a poetic idea, beautiful but unreachable. What we do know, space is not empty. It's alive with structure and subtle energy. It stretches with time. It carries ancient starlight and the hum of the Big Bang. It has no center and, as far as we can tell, no end. The questions that remain still, questions remain. Is the universe infinite or just very large? Is it curved, flat, or something else? Is it one of many, or all there is? And if there were an edge to space, what would be on the other side? We may never find all the answers, but that's not a failure. It's the heartbeat of science. The beauty of the cosmos isn't just in what we know, it's in what we don't. It's in the quiet courage of looking up and asking anyway. The search continues, as it always has, through telescopes and equations, through gentle dreams and midnight thoughts. Every photon we catch, every map we make, every model we refine brings us a little closer, even if the destination keeps shifting like the stars. Maybe that's the whole point. Maybe space never stops, not because it's infinite in size, but because it's infinite in mystery. Maybe it doesn't have to end for it to matter. Maybe it just is, sprawling quietly in all directions, an invitation, not a boundary. You were part of it in the introduction. I asked where you were listening from, what time it was, and whether this question might keep you awake or lull you to sleep. I hope by now you feel more relaxed. I hope your thoughts have softened into that quiet space where wonder lives. And if you're still awake, just barely, I hope you found some peace in the asking, even if the answer remains elusive. Because really, that's what space gives us. Not just stars or silence, but the freedom to ask the biggest questions of all. As we sit here surrounded by stars and bathed in ancient light, we're part of that expansion. Every breath, every heartbeat, every thought you've ever had has taken place on a little rock spinning in the middle of rising cosmic dough. The final thought, perhaps space never stops because questions never do. We're living inside a museum made entirely of light. Every time you look up, You're gazing into a time machine, light that may have started its journey before Earth's first tree, first cell, first breath of atmosphere. And through the lens of science, with the patient help of light, we continue to piece together our origin story, one distant glow at a time. Space is not where things happen. Space is one of the things that happens. And maybe, just maybe, the place you're headed is also the place you started. Only now you've traveled the universe to get there.